Welcome everyone. In this video we are going to prove Snell's formula, which is a formula that helps us to analyze refraction. So let me draw the picture and then give you the formula and then prove it. The picture is like this. We have a surface and here we will have a light beam that comes. And notice, this part is one medium and this part is another medium. So perhaps the green part is the I don't know, water, and the other part is perhaps air, okay? Or the reverse, it doesn't matter. So there are two different mediums. This isn't reflection, this is refraction. In every refraction there is some reflection, but don't worry about that for now. So what does refraction mean? It means that the direction of the motion of our light beam will change. So perhaps it will go like this. As you can see, it would have traveled in such a manner, but since it changed medium, it refracted and changed its direction, alright? And let me draw a line like this. Now we will have an N1 value and an N2 value. I will tell you what N1 and N2 means in about a minute, a couple of minutes perhaps. And then we're going to have our angles. So this angle, and this is the normal line, as you can see. Okay, that is the normal line, maybe put it here. So this angle is going to be I, the angle of incident, sort of. And then this angle is going to be R, the angle of refraction. And notice that these two angles are from the light beam to the normal. Okay, this is very important. So Snell's equation, it is like this. Snell's formula, let's call it, tells us N1 sine I is equal to, and let me put the parentheses, N2 sine R. Okay, this is the formula that we want to prove. And you should be asking, what is N? N is, my friends, called refractive index. And it is defined as the speed of light in space, which is 3 times 10 to the power of 8 meters per second, divided by the speed of light in a medium. Perhaps the speed of light in the air or the speed of light inside water, okay? This is the definition of, so let me write it here even. This is the definition of refractive index. And you can already see that N is greater than or equal to 1 because light cannot travel faster than its speed in space, okay? Because there isn't any resistance, sort of. Alright, so how can we make this proof? To make our proof, I will draw another light beam. And let's say that these two lights are parallel to one another, and I will make this a little shorter so that we have space. So the other light, it is perhaps something like this. This is again another light. It is coming from the same light source perhaps, and since they are parallel, we know that they are coming from a light source that is far away from our picture. Okay, it is perhaps coming from the sun, because parallel light beams means that the source should be far away. Now I am going to draw what is called a wave front. Okay, this is a wave front. This will by definition be perpendicular to our light beams. And this is how I denote perpendicular, a box with a dot inside of it. So we have the wave front, as I said. It is perpendicular. And also let's draw the other refraction. It is perhaps like this. And this is of course parallel with the other refracted light beam. And we again have our wave front. It is like this, and it is again perpendicular. This wavefront idea comes from Huygen's principle. His name is spelled like this. He is Dutch, and I'm not really sure if I am pronouncing his name correctly, but this is the correct spelling. I mean, Huygen is the name, Huygen's principle is the idea that we are using. There is more to his idea, but the wavefront concept comes from this principle. Alright, so how do we continue from this? Well, one way that we can continue is we can note that this angle will also be this. If we draw the normal line here, this will be I and this will be R, right? Well, one thing that we can say is we can say that this angle, let's do it with blue, this angle is going to be I because if you concentrate on this part is 90 degrees, all right? So this is 90, this one is 90 degrees minus I, all right, that's cool. And then this part is also 90 degrees, so there is I left for this part, for that angle. And I want to now give a name to this side. This side will be in orange and it will be named delta x. Okay, cool. It is just the distance. And then I am going to tell you that the light that travels in the N1 medium, the medium with a refractive index of N1, that light has a speed of V1. And the other case, you probably guessed, will have a speed of V2. So if I am interested in a specific time interval, then what I can do is I can say perhaps that this length, this one, will be my velocity times the time that I spent, V1 times delta t. And of course we here assume no acceleration because, there is no reason to not make that assumption. That is V1 delta t. And now I want to also draw another angle. I will call this one R as well. And how do I know that? Well, look at this. This is 90 degrees. So this means this part is 90 degrees minus R. And since all of this should be 90 degrees, there is R left for this little guy. And now I can also write a formula for this length. I can say, let's do it perhaps here. I can say it is going to be our second velocity, V2, times the time interval, delta t. Alright, so now we are ready to start. We did everything that we needed to do. There is only, the thing that's only left is to make our proof. So, if I ask you what is sine of I, then you will say sine is opposite divided by hypotenuse. So if I look at this triangle, the opposite is going to be V1 over delta t, and the hypotenuse is going to be delta x. So if I solve this equation for delta x, I am going to see that, let's do it with orange, delta x is equal to V1 times delta t divided by sine of I. And then if I ask you what is sine of R, then you write sine of R. You again say it is opposite divided by the hypotenuse. So if you look at this red triangle this time, then you're going to have the opposite is this guy, 1 over 2 times delta t. I meant V2 times delta t, not 1 over 2. Forget about it. And it is divided by the hypotenuse, which is delta x. So if we solve for delta x again, we're going to get that delta x is equal to V2 delta t divided by sine of R. And you might be seeing where I am going with this. I want to equalize these two equations because they are both equal to delta x, which means they should be also equal to one another. So let's do that on the new page. We have V1 delta t divided by, let's see, we have sine of I, and this is equal to V2 delta t divided by sine of R. Here we see that delta t cancels. This is great because it was an arbitrary choice that we made and it should not affect the final result. Everyone can choose different time intervals. But on the other hand, V1, V2, I and R, they are determined by the system, by the relative refractive indexes of two mediums, and you will see what I mean by that. So for V, what can I write? If we return to the definition of N, the refractive index, then I can say V is equal to C divided by N. Alright? I just rearranged the definition of refractive index. So this means for V1 I can write C divided by N1. Then we have sine of I is equal to, for V2 I can write C divided by N2, and then we have sine of R. And here the speed of light in the space cancels. It makes sense, okay. And now look at this. This is looking very similar to Snell's formula, right? It is indeed the Snell's formula. So let's rearrange it. Let's multiply both sides by N1 sine I and then N2 sine R. Or do something, and you will get, if you simplify, solve for it, you will get N1 sine I is equal to N2 sine R. And my friends, this is it. Look at Snell's formula that I stated and look at the result that we just got. They are exactly the same. So this is it for this video. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.